Okay, section 2.2, part 6. This is the last bit of section 2.2. So the last couple of videos we looked at Bohr diagrams. They get to be really big, really quickly, really cumbersome. So today we're going to look at Lewis diagrams, which with any luck will make your lives a little bit easier. So Lewis diagrams illustrate chemical bonding by showing only the valence electrons and the chemical symbol. So instead of showing, like normally a Bohr diagram would have the number of protons or number of neutrons, and then would have all the shells, this one is just showing the valence electrons because that's what's important for bond formation, and then the symbol because you can get the rest of the information by looking at the periodic table. So use dots to represent electrons, and you place them around the element symbols at the points of the compass, so north, east, south, and west. And then the electron dots are placed singly, so one at a time, until the fifth electron is reached, and then they become paired. So what that means is if you have one valence electron, you have your symbol, and then you have one dot above it. If you have two valence electrons, you have your symbol, and this is saying symbol X, there is no element X. One above, one beside, so just going around the compass points. So number 3, one above, one to the side, one below. Hello, one below. Oh, my side one disappeared. Okay. Number 4, going to be one at each of the 4 compass points, so just working your way around. And now that we're at 5, it would be like one of each, and then start doubling again. Okay. 6, one of each, and then start pairing them. 7, one of each, and then start pairing them until you're at 7. And number 8, I'm not going to bother doing one of each because they're all full. Okay, so 2 at each point. Okay, so you work your way around, adding one at a time until you're at 5, and then you start doubling up. Okay, once again, valence electrons you can figure out by the last number of each group. So beryllium, group 2, has 2 valence electrons. Carbon is in group 4, it has 4 valence electrons. So same thing, I'll do a couple of these. So boron. Okay, you know what? Boron's right there and nitrogen's right there. I'm not going to do either of those. They're right there. You can figure that out. If we go to aluminum, okay, if you find aluminum on the periodic table, aluminum is element 13. It is in group 3, which tells me that aluminum is going to have 3 valence electrons. Okay, chlorine, symbol is Cl. It's in group 17. It's going to have 7 valence electrons. Okay, so much easier than Bohr diagrams. So much easier than Bohr diagrams. You're welcome. Lewis diagrams can also be used to represent ions and ionic bonds, just like we could with Bohr diagrams. For a positive ion, one electron dot is lost from the valence shell for each positive charge. For a negative ion, one electron dot is added to each valence shell for each negative charge. And then just like with our Bohr diagrams, we're going to put square brackets around it to indicate the transfer of electrons. It's basically showing you didn't make a mistake. This is what I meant to do. So beryllium and chlorine. So each beryllium has 2 electrons to transfer away, and each chlorine can receive 1 more electron. So beryllium donates 1 electron over to chlorine over here, and then its other electron is getting donated to chlorine on the other side. Each chlorine can only accept 1, so you need 2 chlorines in order to fill that transfer. Okay, and then your beryllium is left with no valence electrons. Poor lonely beryllium. Square brackets around it to show that we are showing the Lewis diagram of the ion, and then it has a charge of +2 because it lost 2 electrons. Beryllium chloride, the chlorines each have 8 electrons in their valence shell because they now have full valence shells, and then they've got a -1 charge each. Okay, so things to double check. If the atom gained electrons, is the shell full? If it lost electrons, is the shell now empty? If they're not, you didn't do it right or you didn't complete it. If no electrons have been lost or added, overall you need to make sure that you have total the same number of electrons as you started with, so you didn't just lose some into the ether or magically get more. Did you use square brackets with ion charges in the top right corner to indicate that you have deliberately done this charge. And then do the ion charges add up to neutral? So is your total number of charges, so -1 plus -1 plus +2 is a 0. Okay, draw Lewis diagrams for each of the following ionic compounds. Once again, I'm going to do one of these and leave the other two for you to try. So potassium chloride. Potassium is K, chloride is Cl. So potassium on its own would have 1 valence electron, and chlorine on its own would have 7 valence electrons. Okay, and this one's going to get transferred down there, and they'll be even. So you're going to end up with that as your ionic compound for that. Okay, so any positive ions should not have any valence electrons in them because they now have an empty shell. Square brackets, whatever their positive charge is. Your negative ions are now going to have a full valence shell showing 8. And then square brackets and then a negative charge with whatever value that negative number needs to be in order to show how many extra electrons it got. Okay. We can also use Lewis diagrams for covalent bonds, less messy than Bohr ones for it. So just like Bohr diagrams, you draw your valence electrons to show the number of electrons, and then your shared pair of electrons we usually draw as a horizontal line. So what that means is like these 2 electrons that were being shared, because this one's coming over here, but it's bringing the whole hydrogen with it, we are then representing that pair of electrons by just a line. It gets less messy than trying to figure out getting all your dots in there, especially if you have like a double bond or a triple bond in there. Okay. So carbon dioxide. If carbon dioxide for the Bohr diagram, let's do carbon dioxide for this one. So we've got our carbon. Nope, I went for 6. It's number 6. It has 4 valence electrons. Okay, and then we have oxygen, and each oxygen has 8 valence electrons, or 6 valence electrons, 8 electrons total. Okay, and then we are going to need to basically do some sharing. So like these 2 are going to share with these 2, and these 2 are going to share with these 2. Okay, and then when we rewrite this out, we're going to have carbon sharing 2 pairs of electrons with oxygen, and on the other side it's also going to be sharing 2 pairs of electrons with oxygen, and then oxygen has 4 electrons that are left by itself. Okay, so much better than the Bohr diagram one that we did before. Okay, so much better. Okay, so try the other 2. Let me know if you're stuck. Okay, message on chat, whatever. Diatomic molecules, so things like O2, are also really easy to draw as Lewis diagrams, especially compared to Bohr diagrams. There's a few nonmetals that join together to form diatomic molecules, so di being 2, so diatomic, 2 atoms in 1 molecule, but they're the same thing. The valence electrons are shared. In the case of oxygen, there's 2 sets of valence electrons that are shared. Let me draw it as a double bond. Okay, really important that you know this. There are 7 diatomic molecules. They make up not a real word, but Oberfinkel. It's kind of the only way that you can kind of really pronounce it and have it be anything. So Oberfinkel, hydrogen, oxygen, bromine, fluorine, iodine, nitrogen, and chlorine, all form double bond or diatomic molecules with themselves. So that's how they're stable, like in nature. So the oxygen that you breathe in, O2, the nitrogen that makes up 80% of our atmosphere, N2. Chlorine gas, Cl2. Okay, so diatomic molecules, Once again, I will do one of these. I'll do the nitrogen because I think it's probably the worst one to do out of them. Nitrogen is number 5, so it has 5. Nitrogen is number 7, it has 5 valence electrons. It's in group 5. Okay. Here's another 7, another 5 valence electrons for nitrogen number 7. Okay, and then what we would end up with is some really awkward sharing of electrons. And so the way that we show this is we say nitrogen has 3 bonds where it's sharing electrons with another nitrogen, and then it's got 2 more unpaired electrons, or 2 more paired with themselves unbonded electrons on each of the nitrogens. Okay, so trichlorine, trihydrogen, they're not as hard as nitrogen. Okay, so if you were able to follow along with nitrogen, it's okay. If you weren't, the other 2 are easier. So give it a shot. And then there's an assignment for you to work on practicing drawing Lewis diagrams for elements and compounds.